Hello and welcome to another video. In this video we're going to be going over minimum replacements to sort the array. So you're given a zero indexed array nums, and in one operation you can replace any element of the array with any two elements that sum to it. For example, if you have 5, 6, 7, you can replace the 6 with a 2 and a 4, and it would look like this. Return the minimum number of operations to make an array that is sorted in non-decreasing order, and we have this example with 3, 9, 3. So essentially, you notice that this 9 is not decreasing. So what they're saying is, in one operation, you turn the 9 into a 6 and a 3. So that'd be one operation. And then in one more operation, you turn the 6 into a 3 and a 3. So you would have something like this, and then this would be sorted. And yeah, so elements can't equal each other. They just can't be, less than. And then the other example is 1, 2, 3, 4, 5, and it's already sorted. So pretty much this problem is not too bad. Like once you get first of all, there is a nice little hint they give you with the constraints. So if this is 10 to the 5th, you can't really do anything that's like worse than n log n, somewhere around there, But you have to do something in constant time roughly, or n log n. And so essentially, let's look at this problem in, let's just look at some numbers essentially. So let's just say we have 1, 7, we have 3, 15, and then whatever, 10. So notice that we can't make any number bigger, we can only make them smaller, and we can't move anything around, right? So the only thing we can do to sort these is for example here, if this number ends with 10, we'd never want to make 10 smaller, that would only hurt us, right? We would want to have the numbers to the right as big as possible, and the numbers to the left as small as possible, ideally. So essentially what we're going to do in this algorithm is we are going to go from the end to the start, and we're just going to figure out, do we need to replace our number? And if we do, how do we do that? So let's go through this, and then we're going to have some results. So let's just call that R. We'll make it 0 for now. And we're going to try to figure out what we're doing. So obviously this 10, we're going to go backwards because, like I said, you don't want to make the elements at the end, you can't make them bigger, right? So obviously we could, if we could make this 10 a 20 in one operation, obviously we want to do that, but we can't make them bigger. So we only want to change numbers that actually don't keep a sorted order, but we're going to go backwards to make it easier, and I'll show you why. So for this 10, we're just going to say there's nothing to the right of it, so this 10 is technically sorted. Now for this 15, the problem is it's bigger than 10, right? So we need to essentially break it down into elements that are smaller than 10, but we also need to break it down in as few operations as possible. So we have a 10 and we have a 15. We need to break down this 15 into elements that are smaller than 10, but we need to break them down as few operations as possible. And then there's a couple things. So can we just break it down in 2 operations? Well, we can, right? So we can just break it down. But if we did, what numbers do we pick, and how do we do this, and how do we do this in O1? So obviously the numbers you'd want to pick, and you could think about that, you could pause the video and think about it. So you can break this 15 down into 2 numbers that are smaller than 10, but how would you do that? And what numbers would you pick, or equal to 10? One combination is a 5 and a 10. That would satisfy it, right? So we have 5, 10, 10, that would work. Would you want that though? Is that ideal? Well, it turns out no. And so it turns out you want to try to break down your numbers in the way that, first of all, you want to use as few breakdowns as possible, right? So here we're only breaking it down into 2 numbers, so we're using one break operation. Okay, but we want to break it down into numbers where the min number is as big as possible. And what I mean by that is this 10, 5, the problem here is now that we have to keep going past this, now our number we have to compare to is a 5, which isn't ideal, right? Ideally, we'd want numbers that are bigger, and then that way we can maximize our chances of not having to do anything else. So we'd actually want to break this down into 7 and 8, right? Because that way, then everything over here has to be less than 7, which is a higher chance of that happening than a 5, right? So that's how you would do that. But what if your number was something different, right? What if your number was something let's say it wasn't 15, let's say it was 150. Let's just start with something like that. Let's say it was 150. What would you break it down into, and how can you do that? And this is basically what the crux of this problem is how do we break down our number to satisfy the constraint that it's less than or equal to 10 that uses the minimum operations and ideally gives you like the best possible number breakdown. So it turns out if your number is divisible by 10, the best way to do that would just be have a bunch of whatever your like divisible by 10 is, right? So 15 is strictly divisible by 10, and it would be 15. So we can just write a bunch of 10s. We can just write 10, 10, 10, 10, 10, 15 times, right? And so this 150 would be broken down into 10 times 15 times. And essentially, every break, when you break, so they showed this 3 being broken down, but essentially the optimal break when your number is strictly divisible is just to always break down the number into whatever you need, the 10, and then whatever's left. And so you do that, and then you break down 140 into 10 and 130, and you break down 130 into 10, and so on. So if your number is strictly divisible, how many breaks does that take? Well, it actually takes, if you think about it, every time you do a break, you generate a number. So let's try a smaller number just to see it clearer. So let's say our number is like 40, and we're trying to get it to this. So let's count how many breaks we have. So for one break, we have this. That's one break. Okay, now we have another break, and then we have one more break. So you can see in 3 breaks, we generated 4 numbers, right? We have 10, 10, 10, 10. So if our number is strictly divisible by 10, we can actually write that down. Strictly divisible by the like target we're trying to get. Let's call it target. Then the number of let's call that operations equals number over target minus 1, right? So for 40, it took 3 operations. So it would be 40. All right, like let's show it again. It would be 40, 1 operation, 2 operations, 3 operations. So for 40, this is 4 minus 1. And then what's our like new number that we're comparing to? So let's write that down as well. So didn't mean to do that. So then the new number we are comparing to in the future is still that target number, right? So because our number was strictly divisible, like if we had 40 and 10, then we would just break this 40 down into 10, 10, 10, 10, and then everything to the left would still be compared to 10. So that's a strictly divisible. Now the trickier one is if it's not strictly divisible. So here we have 15 and 10, and we can't break it down to 18 or 8 and 7, but what if we have something like 3 and... or not even 3. Let's say we have like 7, like something tricky. So let's say we have 7 and we have, I don't know, like 22. So this is a good one. So how do we break down this 22? First of all, how many breaks would we need to do? So let's, like the biggest number we can possibly break off every time is a 7, right? So let's just see what happens there. So if we break it, we break 7, then we get 15. You can break it in half, but it turns out breaking in half doesn't make it any better. So I'll show you breaking in half first, just real quick. So if we just have 11, and then we have 11, then we break it in half, you know, roughly in half, 6, 5, 6. So it can be like as good, but it can be worse, right? So it can easily be worse. So breaking in half is not ideal. Like I said, the ideal thing is to break off the biggest number possible, but the problem is it's not quite that simple, because if it's not completely divisible, so obviously when it's completely divisible you want to break it off like that, but actually something like breaking in half makes more sense here because you want your numbers to be as close to each other as possible. So let's see what happens if we break off the 7. Like, so we have 7, we have 15, then we break off another 7, we have an 8, and then we have to make this 8 smaller again, so we have a 1 and we have a 7. And so now the problem is our array is 1, 7, 7, 7, which is really bad because our smallest number is a 1, so anything to the left has to be smaller than 1, which is going to take a shit ton of operations, right? So we want to break it down better, and so the way to break it down is actually, you want to break it down into components that are as close to each other. So I think actually here, to visualize it, would be you would break it down in half. I think that is actually would be the case, but I'm going to show you an easy way to do that. So you would want to break it down into something like this, actually. Because then your numbers is as close to each other as possible. They also equal 22. And now your leftmost number is a 5. So we maximize that, right? Because if we make that, like if we make this a 7, for example, then this would have to be a 4, which is worse, right? So that's kind of like the intuition for when our numbers aren't strictly divisible. So let's write that down. So if number not strictly divisible by target, then number of operations, and let's figure out how many operations we have also, right? Equals, so let's see what we did here. So the number wasn't divisible by the target. So 22 divided by 7 equals 3, right? A lower divide. And then the remainder is 1, so there is a remainder. And it took us how many operations? This is 1 operation, 2 operations, 3 operations. So here it was number over target minus 1. But now if there is a remainder, it's actually just going to be number over target. Let me bring that back in. And let's actually just move over here just so we have more space. So number of operations here is number over target. And we're not subtracting 1. So the only difference is because you have to account for this remainder, right? You have to account for the remainder. So that's why there's 1 more operation. And now what's our actual number, right? Like what's our target? So I showed you how to break this down like this, but actually the fast way of figuring out what are small numbers is actually number divide. Actually, let me think about this. No. It's not number divide by target. It's number lower divide by the number of operations it took. Or actually, sorry, it's not the operations it took. It's like the number of these total numbers here, right? So it's going to be number divided by total amount of numbers that we made. And what is this total amount of numbers that we made, right? So this total amount of numbers that we made is simply operations plus 1, right? So that's pretty much all that is. So now if we combine that together, then our new number that we're comparing to is number lower divide by operations plus 1. Okay. And so that's what also, so for as far as like operations, yeah, I mean, it is technically that for this one. So, but yeah, essentially like, so let's try this, by the way. So this 22, we made 4 numbers, right? So 22 lower divide by 4 numbers is 5. And that would work for anything. So let's try this with something else just to show you. So let's say we have like even something big, right? Let's say we have like 200 and we want to divide it by 3. So it would be kind of hard to figure out how many numbers you make. So let's actually try something else. Let's try maybe like 70 and 15, something a little bit more reasonable. So how do we figure out how many numbers we made? That is the number of operations essentially, right? So yeah, that is the number of operations. It's actually the number of operations plus 1 technically, or the quotient plus 1. So 70 divided by 15 is, I think it's 4, right? So 70 divided by 15 is 4. And so if you think about it, you would break it down, like one way you could break it down is 15, 15, 15, 10. But like I said, this wouldn't be ideal, right? So you do make 4 numbers, but this isn't ideal, right? So you want to figure out like what would actually be the ideal number of doing it. And the ideal number of doing it would actually be 70 lower divide 4, which would be 17. Is that right? I don't think that doesn't sound right. 70, 60. No, I don't think it's 17. I think it's actually I think it is. So I think right, yeah, never mind. This is correct. So this should be 15, 15, 15, 10. So this should actually not be 4, this should be 5. That's a problem. Okay, so we had 5 numbers, not yeah. And I think now, yeah, so now we have 14 as our number. And so now you could see that like we could have broken down this 70 into 15, 15, 15, 15, 10, but actually you want to break it down into 14, 14, 14, 14, 14, and that would make your ideal small number. So now that we know that, so we can kind of get rid of this. I think this is a little confusing. So let's get rid of this part and let's actually rewrite that. So the new number is the old number divided by the quotient plus 1. Because if you think about it, the number of numbers you make is the quotient plus 1, because 70 lower divide 15 is 4, but you also have a remainder. So you're saying you have like 4 full numbers, and then you have one more number with a remainder. So that's 5 numbers technically. So hopefully that makes it a little bit clearer. And so yeah, let's go back. So if the number is strictly divisible by the target, then the number of operations is num over target minus 1. But remember, this could also be probably a little bit easier, right? So if there's no remainder, like what is this target minus 1 equals? Well, let's think about that as well, right? So let's say we had something like 21 and 7, right? So how many operations is that taking? And that took 2 operations. So this actually, target minus 1 is actually, we don't need to do that. It would just be the operations plus the quotient minus 1. So we can even simplify this as well if we wanted to. So let's do that. So let's get rid of this. Not that. Okay, I think, I don't know if I can, I think I should be able to type in here, and then that could simplify. Okay, so there we go. So the number of operations we have is number divided by target minus 1. And we can test that, right? So 21 divided by 7 is 3, but we only had 2 operations because if you see 21, 7, 14, and then one more operation here. Okay, so this makes it a little bit like easier. So the number, so if the number is strictly divisible by target, the number of operations is number over target. Sorry, this shouldn't be target minus 1. This should be quotient minus 1. So this should actually be not number divided by, it's just quotient. There we go. So that kind of simplifies that. And then the number that we're comparing in the future is still the target because it's a clean divide. And then if the number is not, then the number of operations is here. It's going to be a little bit different, right? So it's going to be just quotient, as I explained earlier. So this part should be deleted. And this part should be, just to make it simpler, quotient. Because like I said, if we have something like 22 divided by 7, the quotient here would be 3, and let's see how many operations we took. So let's just say we take 7. Obviously, we're not going to. Or actually, we can even show it like the suggested way, right? So we would split into 11, 11. That's 1 operation. Then we would go 5, 6, and then 5, 6. So that's 3 operations total, and our quotient is 3. So that part is correct. And then the new number is, like I said, this is the shortcut of the new number is the old number divided by the quotient plus 1. So the quotient is here 3, so it'll be 22 over 4. And let's try this with a quick number. I think we did do that. So yeah, 70 here, 70 divided by 15 is going to be 4. So then the new number would be 70 lower divided by 4, which would be 14, I believe. Or sorry, 17 divided by, this is wrong a little bit. So the quotient is 4, and then the new number is number divided by quotient plus 1, right? So it's 70 lower divide 5, which is 14. And as you see, this would add up to 70, so this would be ideal solution. Okay, so let's walk through the rest of this now. Let's clean up a little bit of this, and let's just walk through the rest of this and kind of understand our logic now. So sorry that was a little bit confusing, but hopefully I made it a little bit easier with these like simplifications. And this is what I'm going to be using. So, okay. And you can simplify it as much as you want, but essentially that's how you do it. And so that would be the shortcut, is you literally, once you know this part here, it's really straightforward. Like this part is kind of easy to figure out, like how many operations it takes, but the part with the quotient, it's really tricky. Like, how do I figure out what my numbers are going to look like really fast, right? You can't, like, how do I optimize that? Like, how do I make sure that, you know, like I said, if you have this case, 22 divided by 7, how do I make sure I don't have something like 7, 7, 7, 1? How do I make sure they're evenly divided? And you can't just have some recursive thing that divides, you know, you can't just like be like, okay, let's just keep dividing by 2 until they're less than 7, because that wouldn't be n time, or that wouldn't be O of 1 time. So you literally just do 22 divided by, yeah, the quotient plus 1, so the quotient would be 4 here, and that would give you 5. And then your smallest number is 5. And you don't remember, you don't care about your biggest number, so you don't care if your array looks like this, or whatever. Like, all you care about is the smallest number, because then you're going to compare the things to the left to that. Okay, so now that we know that, let's just do the rest of this, now that we know all these things. Okay. So 15 is greater than 10, right? And so for this 15 is greater than 10, and now can 15, so let's get the quotient. So 15 over 10 is 1, and then 15 mod 10 is 5, right? So there is a remainder, so we're going to go for this one here. So the number of operations is the quotient. So the quotient here is 1, so we are going to add one operation over here. And now what's our like next number? Like how do we split this? Well, it's just going to be 15 over quotient plus 1, right? So 1 plus 1. So 15 over 2, lower divide, that's going to be 7. And so now our new smallest number here is going to be 7, and because this will be split into 7, 8. So now we know that like our new, like once we're over here, the number we need to compare to is 7. And so let's do that. So we're over here and we need to say, okay, is 3 less than 7? Well, yeah, it is. So that's already sorted, so we can ignore that. Now we also need to update our current number, right? So if it's in sorted order, we do need to update our current number to be just whatever number we were on. And if it isn't in sorted order, then we have to figure out how many operations it is and what's our new number, that two-step process. Okay, now over here, we need to actually look, okay, so is 7 less than 3? No, it's not. Okay, well, so let's do that thing again. So what's 7 lower divide by 3? It is 2. Okay, what's 7 mod 3? It is 1. And so we have to look again. Okay, so we do have a remainder, which is going to be this one here. And so if the number is not strictly divisible by the target, then the number of operations equals the quotient. And so the number of operations would be the quotient here, which is 2. So we're going to add 2 more operations here to our result. That's going to be 3. And then what's our smallest number? Well, let's take a look again. The new number is the old number divided by quotient plus 1. So it's going to be 7 divided by quotient plus 1. Quotient here was 2, so we're going to divide by 3, which is going to be 2 here, right, if you lower divide. And that also makes sense because it's going to look like 2, 2, 3 ideally, right? Once again, you'd rather have 2, 2, 3 than this case. That screws everything up because now we need more stuff here. Or you might, like, right? You might not, but 2, 2, 3 is better than the 1, 3, 3 split. Okay. So here our new smallest number is 2. So like I said, it's going to be like this, really. We're not gonna actually get this array. We just need to know that the smallest number is 2. And now we go for this 1 and we say, okay, well, one small and 2, so that part's already sorted. So our result here is 3 because we needed to do one operation here and then we needed to do 2 operations here, right? And that makes sense because we split the 15 into the 7 and 8 in one operation, and we split the 7 in the first split. We can split it into something like this, 3 and 4, and then we can split it like this in one more operation. So it's 2 operations total. So we have 3 total. So once you understand like that you want to go backwards and that you have 2 cases, a complete no remainder divide and a remainder divide, then it's pretty straightforward. So let's actually code that up now. Okay, so we're going to have our operations, which is going to be our result. And then we're going to have the max allowed, which is like the biggest number we can have. And we're going to initialize that to nums -1, right? Because we're not going to, like, this last number is always, we're always going to say it's sorted. We can't make it bigger. Like, we can't make this 12. So if this number is sorted, that means we're going to compare backwards. Okay, so we're going to compare backwards. So we're going to check every element except for the last one. So we're going to say for I in range. For I in range, length nums -2. We want the second last element and then go all the way to the front. So we're going to say the number is going to be nums I that we're going to use. And then we're going to say if the number is greater than max allowed, that means that our number isn't in sorted order, right? So that means we have something like 5-3 or 6-3 or whatever it is. So now we're going to get this quotient and remainder. So we're going to get quotient, remainder. And there is actually a Python function I found called divmod, which is kind of nice. So essentially you give it 2 numbers and then it will give you a quotient and a remainder. So you can say I want num divided by max allowed, and then this will spit out a tuple which will give you a quotient and a remainder in one line, which is kind of nice. So you don't have to do like divide and then mod. Okay. And you could do a divide and mod if you wanted to though. So now we need to check, do we have a remainder? So if we have a remainder, that's going to be that case on the bottom that we had in the picture. So operations is going to add quotient, right? So for example, if we had something like 7-3, in order for the 7 to get broken down enough times, we need to break down the 7 into, like I said, 4-3, which would be 1 break, and then we need to have 2-2-3, so that would be 2 breaks, and the quotient here would be 2. So operations plus equals quotient, and then we also need to do get the new max allowed number, right, which is like the smallest number in our new array, which is num lower divide by quotient plus 1. And this code is a lot simplified, so you could like do it another way, like I said, This is like already pretty simplified, so if you want to make it like a little bit clearer to read, you could use some other variables, but that's essentially how you do it. You literally just say like, if my number has a remainder, then the smallest number is just going to be my number divided by quotient plus 1, just means like how many total numbers do I have. Okay. And then else, so if there is no remainder, essentially you have to do quotient plus or quotient minus 1 breaks, because if you have a number like 9 and you want to turn it into a 3, that will not take you 3 operations, it will take you 2, because for the first one it will go 6, 3, and then for the second one you'd break down the 6 into 2 3s, right? So every single time you generate 1 3, but then for the last time you would break your 6 into 2 3s, so that would give you 2 3s in one operation. That's why it's minus 1. Okay, and then so the other case is the number's already sorted. So if the number's already sorted, we just need to simply take that number and store that somewhere. So actually, yeah, so this is just going to be the else case here, which is max allowed equals num. And then finally, we want to return the number of operations we had. But yeah, I think this problem is kind of like a more of a math-ish problem. It's not super hard to figure out what to do. It's just kind of hard to get exactly like how do I greedily, you know, split my numbers with a remainder into something reasonable really fast. And so once you learn that, then it's pretty straightforward. That if you have a remainder, you're going to be splitting by basically dividing by 2. And then if you don't have a remainder, you don't want to be dividing by 2. You just want to chop off that number every time. Okay, so let's try this. And you can see it's pretty efficient. I think when I was running this, it kind of like varies. So yeah, I don't know. Okay. Well, anyway, so let's go through the time and space complexity here. So for the time, it's pretty straightforward, right? Like we just loop through our numbers backwards, and that's all we do. Everything else is O of 1. So that's O of n. And for the space, we don't use any arrays or anything, so that's going to be O of 1. So yeah, time O of n, space O of 1. And I think that's going to be it for this video, so hopefully you liked it. And if you did, please like the video and subscribe to our channel. And I'll see you in the next one. Thanks for watching.